IE41 virus. Transshipment model. In some cases, it may be better to ship units through intermediate or transient nodes before reaching the destination nodes, as this may result to a lower total cost. This type of model is called the transshipment model, a more general case of the transportation model. Consider the following example. A certain production plant is to accept raw materials at 2 drop-off points. These materials are to be stored at 3 warehouses first before being sent to the production line. Given the transportation costs, how should the materials be delivered to the production line? Transshipment occurs when there are nodes that act as both source and destination, called transshipment nodes. In our example, nodes 2, 3, 4, and 5 are transshipment nodes. Node 1 is called a pure supply node as it only acts as a source, while node 6 is called a pure demand node as it acts as a destination only. Formulating the LP of a transshipment model is very similar to that of a transportation model. Again, we let Xij be equal to the number of units to be shipped from node I to node j, and Cij be equal to the cost associated with shipping a unit from node I to node j, shown already in the figure. Our objective would be minimize z is equal to 2x12 plus 5x13 plus 6x14 plus 5x23 plus 4x25 plus 3x34 plus 6x36 plus 4x45 plus 5x46 plus 4x56. We now subject the objective function to constraints. In general, node constraints have the form inflow is equal to outflow in the sense that all units going into the node will be all the units coming out of the node. Pure supply nodes and pure demand nodes have the same constraints as the supply and demand constraints, respectively, in a transportation model. Pure supply node constraint, node 1. 500 is equal to x12 plus x13 plus x14. Pure demand node constraint, node 6. x36 plus x46 plus x56 is equal to 1100. Transshipment node constraints. x12 plus 600 is equal to x23 plus x25. This is node 2. x13 plus x23 is equal to x34 plus x36. This is node 3. x14 plus x34 plus x54 is equal to x46. Let this be node 4. And x45 is equal to x54 plus x56 as node 5. Finally, we have the non-negativity constraints, where all values of x are greater than or equal to 0. Solving for a transshipment model involves converting it to transportation model by applying the concept of a buffer in the transshipment nodes. Since transshipment nodes act as both source and destination, aside from the original supply, they can provide for the original demand to be satisfied. A buffer is to be added. This buffer is equal to the sum of the supply or demand for the whole model. Remember that total supply should equal total demand. Our buffer for this example is equal to 500 plus 600 is equal to 1100. We can now solve this problem just like how we solve transportation models. We now construct the transportation tableau. Let us look at the supply and demand of the nodes. Since nodes 3, 4, and 5 are transient nodes, the original supply and demand are both 0. However, the buffer value of 1100 is added since they are transshipment nodes. For node 2, the buffer added is also added, making its supply total to 1700 and giving it a demand of 1100. Notice the cost of each path. Infeasible paths have cost of m, a very large number. For transshipment nodes, the cost of shipping to itself is 0, since no shipping actually occurs. We can now solve the tableau using the method of multipliers. Do this for practice. The final tableau is given as... Note how x22, x33, and x44 were given values to balance the tableau. Total cost for shipping is equal to 2 times 500 pesos plus 4 times 1,100 pesos plus 4 times 1,100 pesos is equal to 9,800 pesos.